Okay, welcome all. Hopefully you can hear me. Let me just check that. Yeah, you can hear me? Excellent. So I'm just going to check on my... Yeah, definitely. All right, let's mute that so I don't get confused by the extra sounds. Usually I spend the first few minutes of a live checking the sound by asking if people can hear me. And I decided just to get some headphones and check it myself. So excellent. Thank you so much for joining. Let me introduce myself. My name is Clara, and I am a particle physicist working on the ATLAS experiment at CERN. I'm also an assistant professor at the University of Amsterdam, and I work for Nikhef in the Netherlands. So I've been working on the ATLAS experiment for 14 years as a professional particle physicist, and during that time I got my PhD at the University of Manchester, and then I've worked in a number of different countries, but always with the ATLAS experiment at CERN. So, I'm also simultaneously live on the Clock app for the people on YouTube. We're just having a couple of technical issues there. We'll see if that works, but the main live today is on YouTube, and I'm really excited that today I've turned on the subscriber-only chat, and hopefully that makes things so much nicer for you. That means that people can't come in and disrupt the chat. And we've also got Bob, who is from Fundamentally Explained, and he is moderating the chat. So thank you so much, Bob, for joining and for moderating, which just means that everybody can ask their questions and we can have a really nice discussion. So yeah, thank you so much for joining. I've seen that there's already a few questions in the chat, so I'm going to launch into those in a moment. I have a poll running that asks if this is the first time you've joined one of my lives, because it's good to know how many people are seeing my live stream for the first time. That doesn't necessarily mean it's the first time you've seen a video, or I assume it's not if you somehow found this link. If you do happen to just be passing by and you're wondering what's going on, stick around. We're going to talk physics. So yeah, welcome. So yeah, I see some names also that I recognize in the chat, so thanks so much for joining. I also saw a question asking about interviews. Also, if you're around at Nikhef, come say hi. That would be great. Oh, actually, I should mention, if you're in Amsterdam on the, let me check the date. I think it is, let me check I'm on the right date. 7th of October. If you're in Amsterdam on the 7th of October, or in the Netherlands in general, we have an open day at Nikhef. So come join us and find out more about the research that's going on at Nikhef. I'm not sure for certain that I'm going to be there. I haven't worked out my schedule yet, but we've got some really excellent colleagues who are going to be there and talk about all of the research that they do with you. So you should definitely go and check that out. Okay, the Clock app doesn't want to work. Let's try that again. How was your experience? Not great. Okay, that's gonna try again. It says poor connection. Okay, we'll try that out. But anyway, we're here on YouTube. So please put your questions down in the chat and I will take a look. Oh, I see Jason's here as well. Hi, Jason. So Jason is a colleague of mine as well from the ATLAS experiment. Brilliant. So actually, I put some of the questions already in a Google Doc. So I saw that Eric was asking, does the energy created by the collisions at the LHC go? So given the immense energy demands of the LHC itself, is any of that released energy stored and utilized? So no, we don't store the energy that we use in the Large Hadron Collider. There's some research going on to look into being able to recover energy from an accelerator, but that's not what we're doing at the LHC. The energy is high, but for individual particles, for individual particles, the energy is very high. But the general energy of the LHC beam, the protons, is that of a flying mosquito. But it's just squished down into a very, very tiny space. So the type of energy is interesting. We should also specify, because there's two different uses of the word energy here. one type of energy, we're talking about the electrical use it takes to be able to run these machines. And CERN uses the energy of a small town to be able to do our experiments. And then we're talking about the energy of the particles themselves that we use for our collisions. So our center of mass collision energy at the moment is 13.6 TeV, so that's tera electron volts. And we use this energy in order to be able to create new particles that we're interested in the Large Hadron Collider and study them. So new particles like the Higgs boson that we discovered at the LHC in 2012, but also other types of particles. So for example, different types of quarks and antimatter particles, and potentially, if it can be created in our collisions, also dark matter is something we'd love to be able to create in our collisions and to study at the LHC. But we don't know what it is, so therefore we don't know whether we're creating it yet or not. So, but the energy, to answer the actual question, yeah, it doesn't get stored. The new particles are created in our collisions, and then these particles travel through our detector. So for example, with the Atlas detector, we have a number of different layers and we surround them around the collision point. So the protons come in and they collide, and then the new particles are created and they come off in a sort of firework shape from that collision point. And then those particles are measured in our detector. And one of the ways that we measure them is by absorbing their energy or absorbing them into the detector. Okay, I'm gonna have to stop the TikTok live because it doesn't want to work today. Give me just 1 second to see if I can fix it. Otherwise, we're gonna give up. Okay, one last chance. Otherwise, we're gonna stop. Okay, yeah, so these particles come off from the collision point, they're absorbed into the detectors, and then that energy just dissipates into the detector. So let me see what other questions we have. Also, I'm really sorry if I miss any. If I do miss any of your questions in the chat, then please just post them again a little later, and I'll try and catch as many as possible during this live. Also, if you are watching from the future, if you're watching this live stream later on, then I'm going to try and put some chapter headings down below in the description so that you can find the questions that you're most interested in watching, in case you don't want to watch the whole thing, but you can watch the whole thing if you want to. So I'll try and put a description down with the chapter headings so you can find the topics. I have no idea where we're going to go in this conversation, so that's either going to be really easy or it's going to be really difficult, but we will see. Also, one more thing, if you can like this stream, that's really helpful. So then it tells YouTube that you're enjoying the discussion that we're having and talking about particle physics, and then it might send the stream off to other people so that they can watch it too. So if you can give me a thumbs up, and if you're not already subscribed, then I talk about particle physics, and I'd love it if you stuck around and watched more of my videos. So thanks very much. All right, back to the questions, because that's why we're here. So welcome everyone who's joined. I'm just catching up with the chat as everyone was arriving. So there's a question here: have all of the strange particles created by the proton-proton collisions existed or do exist, or are some of them only the result of CERN experiments? So this is a really great question. Everything we're doing at CERN, all of our collisions, are happening naturally elsewhere in the universe. And we're not even operating at the highest possible energies or the highest energy collisions that have ever happened. The main difference between what's happening naturally and what we're doing at CERN is that we can pick the particles that we're colliding with. So in this case, we pick protons, or sometimes we pick heavy ions. So we can use like oxygen or iron atoms and then take the electrons off and collide those. So we can pick the particles that we're going to collide with. We can pick the energy. What's really interesting with protons is that they are not what we call elementary particles. They're not, we can break them down into smaller pieces. And that means that even though we can pick the energy that the protons have pretty much, we don't get to pick exactly what energy they collide at, which is what it is a challenge then when we want to analyze the data from those collisions. If we were colliding things like electrons and their antimatter particles, the positron, then we would have more control over the energy, because electrons are fundamental or elementary particles. As far as we know, we can't break them into any smaller pieces, and so we can very finely tune what energy they have for the collisions. The problem is that electrons are very light, and this is very challenging when we want to accelerate them to high energies. So every time you bend the path of a charged particle, it gives off energy called synchrotron radiation. And the synchrotron radiation is proportional to the mass of the particle. So the heavier the particle, the less synchrotron radiation is given off. And therefore, if we use more massive particles like protons, or even if we could use muons, then we would lose less energy when we bend the particles around the ring. But there are different ways that we can mitigate for this, that we can fix this in our experiments. We could just build a bigger ring, because if we build a larger accelerator, then that curvature, the bend that the charged particles would have, would be less. So then they would lose less energy as they are bent around the ring. So that's one of the reasons that we would like to potentially go to a bigger sized ring. You could also build a linear accelerator, and then you don't have this problem because they're not changing direction. And the other thing about going to a bigger accelerator is that we can go then to higher energy, because really the limits that we have for the Large Hadron Collider right now are the magnet strengths. We're at sort of the limits of technology in terms of how strong we can make the magnets that bend the protons around the ring. So for the same magnets, if we go to a bigger ring, then we can go to higher energy. And if in the meantime we can also build stronger magnets, then we can go to even higher energies. And then we can explore potentially more massive particles and just different areas of physics, or high energy physics. Okay, so let's keep going on the questions. I'm probably going to miss loads, so I'm really sorry about that. Oh, somebody asked if Marcello asks, do I personally believe that dark matter actually exists? So it's a great question. I believe that we have measured something in our universe that we call dark matter. The evidence for it is very compelling. If we look at the way that galaxies spin in our universe, they're spinning faster on the outside than they should be. We can also look at the way that light is bent as it's traveling towards us, and it bends more than we expect it to, given the visible matter that we can measure between where we think the light source is and ourselves. So there must also be some invisible matter, which is a better name for dark matter, between us and that light source. So there's a lot of evidence that we've seen that dark matter exists. The problem is we don't know what it is. We don't know if it's a type of particle. There's talk about modified gravity. There's lots of different hypotheses for what dark matter is. And we have to approach it from many different sides. So our astrophysics and astronomy colleagues are measuring in space all of the different types of dark matter distributions that they can see up in space. And we're trying to see with the Large Hadron Collider and other high energy physics experiments if it can be created in a laboratory setting. And if it can be created, can we measure it and then learn more about its properties? If it's a particle, can we create it in our collisions? So it's just one way that in science we're approaching these really big questions in physics from lots of different sides. But I definitely believe that dark matter exists. We just don't know what it is. So I don't think I've even gotten to the start of the chat, start of the live yet. Let me go ahead. Marcello says, has this live already started in a parallel universe? I was working with the technical issues, but it's failed, so we're not simultaneously live on the clock app anymore. Oh, so Minnie Moose is asking how I became a physicist at CERN, because they're about to start physics at university and would like to work there. And does uni prestige matter for CERN hiring? Good question. So as I said, I did my undergraduate at the University of Manchester in the UK. And when I was there, I did just the general physics course. I wanted to be able to build my own physics degree. So there's the core lessons that you have to take, the core courses, in order to be able to graduate with a physics degree at the University of Manchester. But then I had a number of options each year that I could add on depending on what I was interested in. And I was mainly interested in astrophysics, in nuclear physics, and in particle physics. But I also took some courses in theoretical physics, so some additional specific theoretical physics courses. We also had to do a lot as part of our core course. And I took a couple of courses on sort of physics or science in context of society. So I did a really interesting course on science in films, which thought was fascinating, learning about how human fears throughout history have shown up in zombie films. That was one of the courses that I took. And also we watched Do Androids Dream of Electric Sheep and analysed a bunch of different books. And I think it's really important to also see how science is placed in society. So that's a bit of a sidetrack, but that's the kind of thing I was interested in at university. And then I also did an exchange program at my university. So my original plan was to do an exchange with a Spanish university because I learned Spanish at school. But I got to university and physics was hard enough in English. So I decided that it wasn't the right time for me to do that. So I did an exchange to Singapore where I could keep studying in English, but also explore a completely new place to me and just travel somewhere really cool to learn about another culture as well. Then I came back and I did my master's degree at the University of Manchester on D0 at Fermilab, which was a previous high energy physics experiment in the US, working on the Tevatron accelerator. And my job was to study top quarks, and I was doing a measurement that no one else had completed before. They'd already done some of the steps before, but it was with a whole new set of data. And so as a master's student, I was able to work on something no one else had seen the answer to before, which was really exciting. And for 2 months during my undergraduate, they said, do you want to go to Chicago? And I jumped at the chance and absolutely loved it. So I spent 2 months at Fermilab as a sort of summer student. It wasn't an official program, but you can, as an undergraduate, you can come and be a summer student at CERN. And I 100% recommend applying for that. I think you have to be in your 3rd year. I always forget. But you should check out on the website about being able to apply for the CERN summer student program. It's funded. It's a really great program in order to be able to learn more about the research that's taking place here at CERN, to get to work directly with researchers. There's loads of lecture courses that take place, and it's just a really fun summer because there's a lot of new people that all come for the summer to CERN to learn what it's like to be a researcher here at CERN. So then I did my PhD. I promise we're gonna go a bit faster. I did my PhD at the University of, brilliant, thanks Bob. So he's put a link in the chat about the CERN Summer Student Program. So I did my PhD at the University of Manchester, where I was working on the hardware for the Atlas experiment. So I was designing and building and testing pixel detectors for the Atlas upgrade. So we'd already built the Atlas detector by then. The LHC had just started running, but we already knew that it was going to be damaged by those new particles, or by the particles from the collisions passing through. And this is happening trillions of times a second. there's so many particles passing through our sensitive detectors in the Atlas experiment that we knew that it was going to get radiation damage. So I was part of a team who were designing a more radiation resistant version of the pixel detector that we could then add in as an additional layer into the Atlas experiment. And I really loved my PhD because it was really hands-on. I don't know if you can hear that bike in the background. I don't have noise cancellation on, so probably someone's having fun. Then, yeah, I was really hands-on. I did loads of experiments at CERN. 3 weeks into my PhD, they sent me to CERN and said, go and meet loads of people and start this experiment. So that was fantastic. And then since then, I have worked in Paris or near Paris in Orsay. Then I moved to Göttingen in Germany, and then I moved to the Netherlands, where I worked in Nijmegen at Radboud University, and now I work at the University of Amsterdam. So I've worked at a lot of different universities in different countries, and it really gave me a great perspective on how physics is done in different places and to build up a network. But I also have friends that didn't move around like that. So if you're thinking of doing particle physics and you're not thrilled by that idea, I've also had friends that have pretty much stayed within the same country or the same university even, and that's possible too. And part of the question was, does the prestige of the university play a role in the CERN hiring? And I would say mostly not. The main thing that is going to play a role in the hiring is whether or not there's a research group at the university and how much experience you can get. And so a bigger university that has, or not even a big university, but a university that has a good research team that's really active within, for example, Atlas or one of the other experiments at CERN, is going to give you opportunities to be able to try out the research, to get involved, to work on the data, to work on the hardware. And that's the most important thing. If you can go to a university, not necessarily for undergraduate, you can do it for your PhD, that can give you that experience, that's the most important thing that is going to help you get a job at CERN. Oh, hi. There's someone who's joining from who went, I'm assuming that you were at the Physics Pavilion at WOMAD. So WOMAD is, I just saw the message on the screen. It's a festival in the UK near Bristol, and we have a physics pavilion there every year, which is really fun. There's an excellent selection of speakers. And for the last 2 years, I've been the host of the Physics Pavilion. So I get to introduce our speakers and talk with the audience and just generally make sure everyone's having a great time learning about physics at WOMAD. So, right, I'm going to go on to some more questions. Oh, we jumped to the end, so I think I've missed a whole lot. Let's have a look. Oh, so someone says, I saw that the Gateway of Science is opening soon. What do you think about it? So the Gateway is a new exhibition center that we're going to have at CERN. It looks like from the outside, it's supposed to emulate the 2 beam pipe tubes that we have in the LHC dipole. And then inside, we've got 4 new exhibition halls. So 1 to do with the accelerators. This is very generalized. 1 to do with the detectors and how the detectors work measuring particles. We've got 1 on the early universe and how CERN is looking back into the early universe. And we've got 1 on, I hope I'm allowed to say this, by the way, it opens very soon. And we've got 1 on the quantum world, which is super exciting. The whole space is really great. I got to see it about a week ago. It's nearly finished, nearly ready for their opening ceremony. I'm pretty sure from the 8th of October, it's open to the public. So if you're visiting Geneva in October or afterwards, come and check out our new gateway. It's super cool. We've also got labs where you can do science experiments. There's going to be a huge new auditorium, a restaurant that people can use that's at the sort of entrance to the CERN site. And it's just going to be a really nice space that you can come and visit. It's free because CERN is funded by the public, and therefore everything that we do is given back for free because it belongs to you. So I think it's fantastic, and I'm really excited to see it full of people asking questions about how our universe works. So, great question. Oh, so somebody says, can we make quantum entanglement as a high-speed internet? So that's a good question. It's not really my expertise. Um, I know that I don't know, but that would be cool if it can be even faster internet. I think so. I don't. I don't know, but that's a great question. Oh, so Felipe is asking, I'd like to ask how the role of data science and machine learning forecasting techniques could help the researchers at CERN. So I really love this question because I was using machine learning for my master's thesis back when I worked on D0. So that was 14 years ago. And even then, it was already something that was quite well used within high energy physics. So we were early adopters to machine learning, but in the last sort of 5 years, it's really taken off, and there's a whole new set of techniques and algorithms that we can use to help our research even better. So the main way that we were using machine learning was to isolate signals in our data that we're interested in from what we call background events. So what we'll do is I was talking about those collisions, those proton collisions. They come in, create lots of new particles that come off into our detector. Quantum mechanics decides what those are going to be. As I said, we can kind of change, especially for protons, we can change the energy a little bit, but we don't really get to choose what's made. So we get petabytes of data. Really, it's a huge challenge for teams at CERN to be able to even record the data, and we cannot possibly record all of the data from the collisions that are happening in our experiment. So we capture as much of it as possible. We make decisions over which data we can store, and just because we're not arrogant, we don't. We also keep a random selection just in case we're wrong, and later we can look at the random selection. And so we keep as much data as possible, and then there are hundreds of different teams who are asking different questions. So the Atlas experiment, for example, is a collaboration of over 5,000 people from over 100 different countries around the world. And these people they all have different questions about the universe that they want to ask. So we split up into smaller teams. And for example, one team might be saying, I want to look for dark matter, and I think that it's made in this specific way. So they have a theory or a hypothesis about how dark matter could be created in our collisions. Or for example, another team wants to search for the Higgs boson before we had discovered the Higgs boson. And so what each team will do is that they will chop up this data set into smaller pieces by making selections. So for example, if we're looking for the Higgs boson and we want to look for it changing into 4 muon particles, then we can look for 4 muons in our data. And so we can already make that cut in the data, and then the rest of it we call background. And so we're making all of these decisions with the data that we have, and then we simulate also what we think it should look like given our current understanding of the data. And if, for example, we're looking for dark matter, we can simulate what that would look like depending on the way we think it would show up in our detector. And welcome. So someone's just joined the chat or joined the live stream. So we collect all this data, we chop it up in different ways, we simulate different ways we think it should look, and then we try to compare our simulations to the data. That's a really rough way that we can look for new particles. Using machine learning, we don't have to make necessarily these cuts so, by hand. We can train a machine learning algorithm on our simulations and say, this is what we think it should look like if this dark matter exists. Now isolate the data in the same way and look for more events than we would expect just from the standard model background. So that's one way that we're using machine learning, is that we're speeding up that process of isolating the signals that we're really interested in studying. But we're also using it for, so one of the other ways that we're using it, which I'm involved in and Bob's involved in, is anomaly detection. So we want to look for a signal, but we don't specifically know what it looks like. We don't know what dark matter looks like, how it would show up in our data. So instead, what we do is we train the algorithms on everything we know about so far, and then we ask it to look for something different, just something strange. And it's not as precise as training it on the specific hypothesis, but we can do it much more broadly. So we can take a look through all of our data and say, is there anything weird in this data that you haven't seen before? Please tell me, and we can look in that area. So that's another way that we're using it. We're also using machine learning to try and help our selection of events. So these events that are happening, we can use machine learning to help us save more data or save it more efficiently. And there's a bunch, everybody's so, you put a bunch of people that are just really excited about using technology and software and developing it, and just let them use it in scientifically interesting ways, and they come up with lots of different ways that it can help us in our research. So it's a really big field, and lots of exciting things are happening. Okay, so George was asking, one thing that they say they don't understand is, what does the vacuum have so much energy and virtual particles, and what is the role of the virtual particles? So yeah, there's no such thing as, so even in completely empty space, it's not empty, and there is the vacuum potential within the universe that means that virtual particles can just pop in and out of existence. Maybe not my lamp over there. And there's not really any role to it. It's just how the universe is. There's a really interesting way to use this. Use the fact that virtual particles exist. So when there's an experiment at Fermilab called the G-2 experiment, and you may have heard of this because there was lots of talk recently about potentially a fifth force being discovered. It's not been discovered, but they have done a really exciting measurement that could lead to a discovery. And they're doing a measurement that's this sort of indirect measurement that I was alluding to with the sort of anomaly detection of machine learning. They're measuring muons in an accelerator. So they take muons and they accelerate them around, and muons have a wobble, and you can measure that wobble. And specifically, you can predict how much it's going to wobble depending on all of these virtual particles. Sorry, I just saw a really nice comment saying that my style is very refreshing. I really appreciate that. So these muons wobble, and we can predict how much they're going to wobble depending on all the particles that we already know exist, and all these virtual particles that pop in and out of existence around the muon. And we can really precisely measure it with this experiment G-2. And the measurement of the wobble doesn't quite match the prediction from theory. There's a slight multiple decimal place difference. And that hints that maybe there are new particles that we haven't accounted for in our theoretical prediction of the wobble that are influencing the wobble of the muon. So if that's true, then there's a new force or a new particle. The thing is, it could just be that we need to get better at doing this prediction. It's extremely complicated to do. There were multiple people who came together who spent a lot of time working on this to make this prediction, but it could be that the prediction needs further work. So it's a really interesting result, and I'm very excited to hear more from the experimental measurements and the theoretical predictions, but we need more of both to be able to say for sure yet whether or not there is a new force that has been measured. So it's one of those experiments where we say stay tuned, and we'll find out more as time goes on. Oh, Oh, sorry. Sorry. Do you do interviews? Yeah, sometimes I start a question and then I go off in a different direction. Yes, I'm very happy to do interviews. And I put a business email on my YouTube channel. I don't know if I'm going to regret saying that in a video. And also, since you're at Nikhef, you should be able to work out how to find me. I hope that's not too cryptic. But you should be able to find out my email address from there. I don't want to put it publicly in a video, but hopefully you can find me. Otherwise, you can send me a message. Actually, probably the better way to do it is send me a message on Instagram too. So I do check all of my messages on Instagram. I can't reply to them all, but I really, really try to reply to as many as possible, and I will look out for this one. Oh, so there was a question here, I guess, when I was talking about larger accelerators. I'm really behind. What I might have to do is just jump ahead in a minute to the end of the chat, and then if I missed your question, just put it again in the chat, because otherwise I'm really sort of 20 minutes behind the chat. But there was a question here about the FCC and whether or not it's a useful project. So the FCC is called the Future Circular Collider because we're terrible at naming things. I'm not sure whether we're going to give it a new name if it gets built, but hopefully we'll find a different way to describe it. And it's a proposed larger accelerator to the LHC. So it's just one potential accelerator that could be built in the future. And it would hopefully be able to collide particles at even higher energies. But there's a lot of discussions happening now in the community because these projects take a long time to build. You know, they do take resources, and multiple countries come together in order to be able to build these projects. And so we have to make sure it's exactly the one that we as a community want to build, and it's going to give us the most opportunities to explore new physics. So it is a really useful project because it will get us to even higher energies, but we haven't yet decided certainly that it's the one we want to build. There's also potentially linear colliders that have been proposed, and there are different places that these could be built. Also, muon colliders have been proposed, so these would be muons are the heavier cousins of electrons, and if we can accelerate them, then we get that really nice feature that muons are elementary particles, but at a higher mass, and so therefore we lose less synchrotron radiation as they go around. But everything still needs to be discussed, and nothing has been decided yet. So you'll hear lots of different people who have preferences. I'm not going to give my preference here because I'm still thinking about it and discussing with my colleagues about which one I would like to see built. But honestly, I think there's so many questions that we still have open in physics. We have no idea what dark matter is, and we're still exploring the difference between matter and antimatter. Gravity is not in our, we don't have a graviton, for example. So there's lots of things that we're still trying to answer within particle physics. And potentially if this G-2 experiment does show that there's something else that exists in our universe, a different new force or particle, then we'd really want to know what it is and to explore its properties. And on top of that, it's not just about discovering new things, it's about measuring what we've already discovered in as much detail as possible. So my research is mostly not on discovery, but on precision measurements. And I focus on the top quark, which is the heaviest particle that we've discovered in our standard model, our recipe book of the universe. And it's really interesting because it can tell us a lot about how quarks work and also how it interacts with other particles. So for example, how it interacts with the Higgs boson. But it can also potentially help us look for dark matter. So precision measurements are really important as well as discovery measurements. Okay, I'm going to jump ahead because I saw a cool question that I want to answer now. Though my screen. Okay. So yeah, I saw this question that I really want to answer. Can neutrinos from space interfere with experiments? So neutrinos are pretty much not in our experiment. They are so unlikely to interact with you that if you put your thumb out in front of you and look at your thumbnail, there are about 1 billion neutrinos that are traveling through your thumbnail every second. So there are trillions of them passing through you right now, and they almost never interact with you. So in our experiment, we can pretty much just ignore cosmic neutrinos. They're not going to cause any interference with our measurements. What we do have to account for are muons that come from cosmic rays that are interacting in our atmosphere. So we get particles from outer space that come and interact with our atmosphere and create lots of new different types of particles. And one of them are these muons, the heavier cousins of electrons. And one of their properties one of the properties of the muon is that it can travel quite a long distance through the Earth or through the atmosphere, but it does also interact. And when they pass through our detector, they leave a trace in our detector. So we have it like this cylinder that's about this big. Well, not this big, that's this shape. If it was this big, it would need to be in a massive cavern. And the cosmic rays come from above, or from, well, all angles, but mostly from above in this case. And they leave lines through our detector, which then interferes with all the particles in terms of being able to measure all the particles that come from our detector. It's one of the reasons that we put the detector underground, because it helps reduce that a little bit, but it doesn't stop it entirely. When we're running, they're quite annoying, but we have algorithms that we have designed in order to get rid of most of them, so it doesn't degrade our measurements that much. But when we're not running the LHC, they really help for calibrating the detector. Because they leave this nice line through our detector, when the LHC is off, we can turn our sensitive detectors on and measure all of these muons coming through and be able to calibrate exactly the position of all of the different detectors. So cosmic muons from cosmic rays are really useful. Cosmic neutrinos we can basically ignore. But there are other experiments, high energy physics experiments, like IceCube. They're measuring these neutrinos coming from outer space. And there's just some really fantastic science going on that's being able to look at the sort of cosmic glow of neutrinos in space. And one thing I would love to be able to do with neutrinos, not me personally because it's not my research, but to be able to see with colleagues, is we have the cosmic microwave background, which is this afterglow of the early universe. And it's the point in the universe where it first became transparent. And yeah, it's sort of the history of the universe and as far back as we can look with photons. But neutrinos were not confined in the same way. And so, because they pass through most things, and so if we can really look at this proper glow of the neutrinos, we can look even further back in time to the earliest parts of our universe. And I just think that's so exciting and so interesting. And if we can, gather more information about neutrino measurements from cosmic neutrinos, that would be really cool. And so, there's IceCube that's currently operating. There's also other experiments that are studying these neutrinos. For example, one of them is KM3net. So this is something that we're working on at Nikhef. And they are going to put sensitive detectors in the Mediterranean Sea to be able to measure neutrinos there as well. Oh, somebody says, why live now? You have to go to sleep. Jack, I think you should go to sleep then and watch the recording later. I think that would be better. And I will go live another time, hopefully when it's a slightly better schedule. So Rick says, is it loud when you're running the detector? It's pretty much generally got this background noise, mostly of the electronics running and the cooling that we have. So when I go down into the cavern, I've done a couple of lives from down there. Actually, this is a great time to plug it. Thank you very much. So I did a great live with, I say great because I had great company. And so Dylan, one of my colleagues, did a live with me in the Atlas Cavern, where you can, so that's on my YouTube channel. And you can, I think you can hear from that background noise. Yeah, it's pretty noisy in the cavern, also because my microphone didn't work then. So you can hear that kind of background hum of the electronics. But the actual collisions themselves don't make a noise. We can't hear them. I would say you wouldn't be able to see them if you were in the cavern, but you absolutely cannot be in the cavern when the LHC is running. because there's just too much instantaneous radiation. Oh, so thank you. So Bob's going to link that video in the chat. So thanks so much, Bob. So Jeremy is Jeremy is asking, have you always been interested in physics right from a kid? I think I didn't know what physics was as a kid. I knew what science was. I knew what astronomy was because it's very well advertised. I was interested in how things worked. Just in sort of, I had a computer game when I was a kid called How Stuff Works, and you could just explore and ask questions and learn from that. And so I was just generally very curious, and I loved, as many people did, looking up at the stars and wondering what was going on. And so I was always very curious, but I didn't know what physics was for a really long time. And in fact, quite embarrassingly a long time, because we didn't make that separation in my school. We just had science. And so I was learning science. And I think I knew what biology and chemistry was before I really understood what physics was. But I also really loved English and drama, and a lot of those kind of lessons where I got to be a bit more interactive. But ultimately, when I was picking my career, I wanted to be able to go into a lab and to be able to experiment and ask questions and learn about how things work. And for me, things like literature and stuff I wanted to read was still accessible, that I could sort of read in an armchair way. So I wanted to go into the lab and be a physicist, but I didn't know what kind of physics when I started university. I was mostly just exploring all of it and trying to work out what I wanted to be. And it was only as I started doing my master's that I really got hooked on particle physics. And partly one of the reasons, apart from just the physics and the incredible questions that we can ask, I really love the international aspect of it. I love working with people from all over the world and being able to travel as part of my work. And I'm just reading questions as they come up on the screen. And I think that's one of the really best things about this type of research, is that I get to ask really big questions about the universe and work with people from all over the world. So we've got people in the chat who are joining for the first time, so welcome. Thank you so much for joining the live. So we're talking about particle physics. We've been going already for about 47 minutes, and I have not answered everybody's questions yet. I'm really sorry. So I'm going to try and do something a bit more quickly, and then we'll see how we get on. Linking to what I just said, Bob says, so amazing that CERN began in the 1950s. Any historical insights? So the great thing about CERN is that it was set up as a scientific center for peace after World War II. It was to bring European scientists back to Europe and to be able to research things that were for a peaceful purpose. So I think for the historical aspect, that's one of the great things about CERN, is, like I was just saying, people from all over the world, people are working together. Notifications on my phone, should have turned those off. In a peaceful way. Okay. Oh, so Rick's saying, is there a short time that you get to study the data? No, so we record as much data as we can. If we don't record it, it is gone. It's disappeared. We'll never get it back. We have to do more collisions, but you never get exactly the same thing again. And then once it's recorded in our data centers, we have all the time in the world to analyze it. So we collect the data in sort of batches depending on the year or on the run that we have. And then, because that's similar conditions for the detector, and the simulations can be designed to match those conditions, and then we can analyze it. And some of these analyses that we do take years to get out. So some of the analyses that we publish, people have been spending months and years to be able to understand the data. Because the biggest challenge is really, we have to understand our detector precisely for every different scenario that we're looking at. We have to account for particles can be very tricky, so they don't just pass through and we know exactly which particle that was. Sometimes they can look like each other in the detector, so we have to be able to distinguish them in the detector. Neutrinos that I was talking about, we cannot measure neutrinos in the Atlas detector. So there are now experiments at CERN that can measure neutrinos, but not link it to the events that we're measuring in Atlas. And yeah, so they just leave our detector as missing momentum, and that creates a lot of challenges too. So it can take a very long time to study this data. So Sanchez is asking, can a neutrino transform into a photon? No. So there are specific rules in how particles can change into each other, and neutrinos can't turn into photons. Yeah. So Saturn 5 says, were you afraid of the dark sky as a dark sky at night as a child? I was. So I wasn't. The times when because I lived in a city, so I didn't get to see the stars all the time. Mostly we had street lamps a lot of the time. My tea's gonna be very cold now. The times that I actually got to see the night sky, I just found it absolutely breathtaking. The best time wasn't as a child, but the best night sky I've ever seen is on a boat in Malaysia, just completely away from any other lights, and it was just incredible. So Rick's asking, do I teach anywhere? So yes, I'm an assistant professor at the University of Amsterdam. So I get to work with undergraduate students in our practical labs, which is a really great teaching experience because we get to work in the lab hands-on on different particle physics experiments. So yeah, I teach at the University of Amsterdam, and I also make videos online, so I can share what we're doing with anybody who's interested and wants to watch the videos. So this live stream is a little bit of a test too, because I was going to say if it goes well, but I think it's been brilliant. The chat's been really nice, so thank you so much for all of your questions and all of your interaction. So I'm going to try and do more of these as well. So I'm going to try and set up a more regular schedule so we can just drop in, talk to each other, ask physics questions, get updated on the latest physics. And I also make videos, so mostly shorts at the moment, mostly short videos, but I'm also working on longer videos as well. So Tipcentric says, I hope that's Yorkshire tea. I wish it was. Unfortunately, it's not always easy to find when I'm out of the UK. So this is inferior tea, but if it was Yorkshire tea, I would be very happy. Oh, so Imogen is asking, is it necessary to speak multiple languages for a broad study? So I didn't speak, I learned Spanish at school, but not well enough to learn physics in it. So I chose to do an abroad study in an English-speaking university, which was really interesting for me because it was so far away. But I have friends who learned, for example, French at school and then went to a French university, and then it's absolutely necessary that you have to speak it there. In terms of being able to do particle physics, you don't have to speak any other languages. I have many friends who have gotten by perfectly fine only speaking English, but I don't recommend it because when you move to a new place, or if you're at CERN and you're in a French-speaking country, it's nice to be able to speak French with the people that you're living around. So I think it's really good to learn other languages. It's also a really great way to learn a new culture. But you can, if you only speak English at the moment, don't let that stop you. Absolutely study physics, come to CERN, and then pick up the languages when you get here. Oh, so yeah, Joel asks, can dark matter be used as a weapon since it's really reactive with regular matter? So I think that you mean antimatter in terms of it being really reactive, because matter and antimatter, when the counterparts come together, they annihilate and create photons and a lot of energy, and potentially it could be, but it's not the most efficient. It's really hard to make antimatter. We cannot store it. And sadly, as a species, we've got far more effective ways of doing that. So it's not efficient. What would be really cool in the future, and it's touched upon in a lot of science fiction shows, is to be able to use antimatter as a means of transport. So if you can direct the energy coming from the annihilation, then you can use that for propulsion, possibly. This is all hypothetical. And that would be really, really interesting. But again, you need to be able to store it, because if you have a matter container and the antimatter touches your container, then that's going to annihilate, and it's not going to do it in a controlled way. Dark matter, we don't know what it is. So we have no idea. It's not very reactive, because otherwise that would be one way that we'd be able to see it. So probably not, but we don't know what it is, and we don't know any of its properties. Thank you very much for the nice comments in the chat. I appreciate it. Somebody says, so when can we expect to see Loki? Apparently there's a season 2 coming out. I'm pretty sure that's not what you mean, but I'm excited about that. So Felipe says, thanks so much for joining the live. Yeah, that you like the live. That's okay if you need to leave. I'm probably going to wrap up soon-ish because it's getting late. And I'm going to try and do more of these, so we'll answer more questions. And also, if I didn't get to your question, I'm really sorry. You can put it down in the sort of chat for this video once it's finished, or I'll come and check the live stream and try and answer as many questions as possible. I don't know what Scopus is. I'm going to have to Google that one. So there's a question about time dilation and length contraction, so that the speed of a particle remains the same for it and an observer. So the thing about time dilation is that the speed for an observer of a particle that's traveling very fast. Oh, I see what, yeah. It's been a long, let me think about that one. It's probably one of these questions where I think about it and I'm like, oh, that was very obvious. But it's not part of my daily work. I'd have to do the actual maths to confirm it, so I don't look silly on the internet. But let me just explain more generally. When a particle is traveling extremely fast, so close to the speed of light, then the particle, the length contracts for an observer. This is all, I explained this recently. Okay, so we've got a proton traveling very fast, and you've got somebody in the control room. So for the person in the control room, the particle seems to be going at a slower, its clock seems to be ticking slower. And we can actually verify this. We've already been able to verify it in lots of different ways, but one way we can is those muons that I was talking about that are coming from cosmic rays, they actually only last a short amount of time. So they shouldn't even be able to reach us down on the surface of the Earth when they're created in our atmosphere. But because of time dilation, they seem to last a lot longer than we would expect them to if they weren't traveling. For them, it seems like the distance from the atmosphere to the Earth is shorter. And so they experience a shorter distance, and they think they've traveled the same amount of time. They don't think that they're, to them, the observer in the control room seems to be going by very quickly. Hopefully, I'm gonna give you a more detailed answer down in the comments. Oh, so somebody says, I convinced my parents to bring me to Geneva, but only for one day only. I need to visit CERN. Can I be sure to get a tour if we show up there? So if you want to come and visit CERN, absolutely. Unfortunately, we cannot guarantee a tour, but the best way to make sure you get on a tour, make sure you check the website. So we have the CERN visits website that gives you all of the information. You have to turn up about 2 hours before the tour that you want to go on. Hopefully, if you're coming after October, then you'll be able to, thanks Bob, putting the link in the chat, perfect. You can wait when you get there. You queue up, you register your tickets, which are free for the tour, and we've got different visit sites that you can go on. And then you have to wait for about 2 hours, so then you can go around the museum and have a look at our brand new exhibit. and then go on your tour when it's ready for you to go. So I see someone's heading off to bed. Thank you so much for joining. I really appreciate it. If you turn up earlier in the day, then you have more of a chance to get on a tour, because if you miss the one first thing in the morning, then you can just join the queue for the next one. And then also, yeah, if you're coming a little bit later, then we'll also have this new restaurant open, and also super new gift shop where my t-shirt is from. if you fancy an I Heart CERN t-shirt. Yeah, so I really hope you get on a tour. I will warn you though that with the LHC running, it's not possible to go underground. So I just want to make that so you know in advance if you've only got one day there. But our tours, we've got so many fantastic tours above ground that you can go to while the LHC is running. So Joel is asking if we work with fusion reactors. So we don't. That's not our research. There's lots of really fantastic research going on into fusion, but it's not our focus. So there's loads. I love this question. Okay, our universe is only 13.8 billion years old. Then how can we see 46.1 billion years old light using a telescope? So the thing is, it's not 46.1 billion year old light. I don't know the exact number. But it's 13.8 billion year old light. But because of the expansion of the universe, and not just the expansion, but the accelerated expansion of the universe, the distance between everything expands, and it can expand even faster than light. The light that reaches us is much further away than 13.8 billion light years away, but it's only 13.8 billion years old, and it's because the distance between everything has stretched due to the accelerated expansion of the universe. It's really interesting, and yeah, there's also a really amazing feature that Astro Katie Mack, I found out first from her, that you would expect that the further things away are from you, the smaller they are. But actually there's a point where things are so far away that they actually seem bigger to us. And that's because when the light left that galaxy or star, well, not star, yeah, probably a galaxy, it was much closer towards us. And so the light starts traveling and it's a certain size, and then the universe has expanded in the meantime. And so actually these galaxies look a lot bigger than they should do, and that's because they used to be a lot closer to us. It's just a really cool phenomenon that Astro Katie gets absolutely excited about, and is really cool. So I learned it from her, and it just blows my mind, and it's just a really cool feature of the expansion of the universe. So there's a question, can light be a particle or a wave or both? It is both. It's a really cool physics phenomena as well, called wave-particle duality. And Bob's doing a mind-blown emoji in the chat. So yeah, I'm gonna have to wrap up soon. There's really great questions. Also, there's some fantastic ones that I just don't have the time to go into right now. I feel like we could have a whole live just on that topic. So I'm really sorry if I missed some of your questions. Please, again, put them in the chat, and I will get to them later. Oh, so Imogen is saying you can use magnetic fields and a vacuum to store antimatter. Yeah, exactly. So we need a vacuum so that the antimatter doesn't collide with matter. It can still happen due to virtual particles, but it's less likely to happen. And then the magnetic fields, if they're charged antimatter, can hold them in place, or even if they have a spin, then they can be held. But the problem is, if you want to move that, if you do this, then it's really hard to keep those antimatter particles in place. So there's a question, any link between CERN experiments and the development of fusion technology? I don't know direct links, but I'm sure there are. So I'm gonna have to go look that up afterwards. We're both doing sort of this new science that's never been done before, and we have to invent a lot of technology to be able to do our research at CERN, and also for fusion technology, and I'm sure there's overlap between the two, but it's something I don't know as well. Okay. All right, I think I'm gonna wrap up here because we could keep going, but also I have to be up early to go into the lab tomorrow. So, oh, thanks. Somebody says that I hit 6,000 subscribers. So thank you so much. I really appreciate it. Okay, and so Elena, I'm going to finish with this one because it's a really great one to finish on, and then I'm going to try and answer as many questions as possible later as well. So the question is, any advice for someone who just started to study their degree in physics? What can we do to arrive to CERN if we start from a small city? Yeah, somebody says that I should have another mod to cherry pick the questions. I think my original plan also was to try and get some questions in advance. And to have them all written down so it was easier. But I also wanted the interaction. I wanted people live to be able to ask questions. But you're right, it would be good to have another way to pull them out so I'm not spending so much time reading. Yeah, so if you are from a small city and you've just started your degree in physics, so if you want to come to CERN, the best thing you can do as an undergraduate is apply to that summer student program. So we had the link in the chat before. And I'll also put the link in the description later for anyone who's watching later. Apply to be a summer student. If you can try and get some experience in a research group at your university, if you can during the summer spend some time in the lab, just learn about what they're doing, that will help with your application to be a summer student. But even if you don't get to be a summer student, don't worry, because I didn't get to be a summer student. For various different reasons, I didn't apply because I didn't know it was funded, which it absolutely is. So they fund for your time at CERN, whereas I worked during my summers to help pay for university. So I didn't apply, and also they told me it was very competitive, and so I internalized that and just thought, oh well, I'm not going to get in anyway, so I'm not going to apply. But really, my advice is, give yourself the chance. There are so many things that you might think you don't have a chance with, but absolutely you do. And you'll never know if you don't apply for them. And unfortunately, with this type of career, rejections do happen. So it's really important not to take them personally, not to take them internally, and just to keep trying as much as you can. Apply for that other position, apply for that other internship. I feel like that applies more than just to CERN. But it's so many, there is a lot of competition, but you should just absolutely apply and give yourself the best chance. So yeah, the summer student program is the best thing to do as an undergraduate, and then ask research groups if you can intern with them and get some experience in the lab. That'll be really great for a CV when you're applying for other things. And then if there isn't a research group at your university working at CERN, then try and look at other universities for your PhD, or try and look at them anyway. Have a look in different countries if you're willing to travel. You should absolutely be paid for doing your PhD research. It is a job, so make sure that you are getting paid for that kind of research, and make sure that when you're picking a PhD supervisor, that you have someone who is going to support you in your development as a future researcher. Somebody who is going to spend their time giving you opportunities and advising you and giving you, a chance to go out there and explore the different types of physics that you're interested in. So that's probably a really nice topic to end on. Thank you so much for joining. I really appreciated everyone here. It's been such a lovely chat. I think I'm going to keep this up for future lives as well, so that we get, really nice conversations, which I've really enjoyed. So yeah, I'm gonna close it up. Thanks so much for joining, and I will see you in the next live or in a future video. Thanks so much. I have to give a pause because I know if I press the button, then it's going to cut out the sound.